evening. Welcome everyone to our Forest, Fire, and People webinar series, brought to you by Colorado State University's Center for Collaborative Conservation and the Institute for Science and Policy. I am Kristen Uhlenbrock. I am the director of the Institute for Science and Policy and also your co-host in this series. Before we get started this evening, I do want to acknowledge with respect that I and our guests tonight reside on the traditional lands of 48 Native American tribes who now live throughout the American Southwest, Great Plains, and Rocky Mountains, including the Southern Ute, the Ute Mountain Ute, the Arapaho, the Cheyenne, the Apache, the Comanche, the Shoshone, and the Washoe tribe. We also want to acknowledge that many were impacted by the fires of 2020, including losing their cherished homes, seeing forests that they loved burned, as well as experiencing health impacts from the smoke, not to mention everything that was going on with our COVID-19 pandemic at the same time. We are not going to be spending a lot of time on those personal stories about last year's fires, but we will be touching on some of them, and our hearts do go out to those of you that were affected. This is a four-part series, which we're really excited to be kicking off tonight here on Monday. It will be every Monday evening at 5 p.m. Mountain Time for the next 4 weeks. So mark your calendar, same time, same place for the next 4 weeks. We're going to be asking big picture questions, as well as diving deep into the complexities of the intersection between wildfires, forest, and we as humans, and how we play a role in both being affected by and impacting the fuel and the fire. We're going to be looking at the science, including the ecology and the role of weather and climate. We're going to be looking at the management and the policy, the economics, the social considerations, as well as the role of traditional use and knowledge, among many other facets to this topic. We hope the series will spark a little bit of curiosity in you, as well as potentially provide you with a new perspective that you hadn't thought of before. We're going to do our best to take as many questions as possible. So if you're familiar with our webinar series, we encourage you to open that chat if you're joining us here on Zoom and chime in along the way. We have eyes on those questions, and we will do our best to incorporate as many as possible into our conversation. But I will say up here at the very top that we will not be able to answer all of your questions or get to them, but we do love to see them, and they definitely shape future episodes and what we talk about. And we'll do our best to potentially provide you with some more resources to follow up afterwards. We are recording this, and there will be a transcript made available afterwards that you can share. So let me go ahead and welcome and bring in my co-hosts. For those of you who remember us from the Wolf series, I am really excited to be partnering with John Sanderson from the Center for Collaborative Conservation. Good evening, John. How are you tonight? Oh, John, you're on mute.
It's yeah, the saying of the pandemic, you're on mute. So anyway, thank you, Kristen, and thanks to all of you who have chosen to spend an hour of your evening with us. You know, like wolves, fires in Western forests are a complex mix of science, policy, culture, and ultimately on-the-ground actions. And these fires affect all of us. Some of us, as Kristen mentioned, very directly, and most of us, at least in some way, indirectly through federal and state spending, and because the water that comes out of our taps comes from our forests. So we're hoping that this series will give you a little bit of more information to understand the complexities and nuance of forests and fires, but then also when you have to make any decisions about, you know, how you want to help us move forward as a society to deal with these issues, that you'll have information that will help you make decisions you need to make. Unlike wolves, you know, fires tend to be a lot less controversial because we all want to deal with them, but they still require a very high level of collaboration because the scale of the problem is so huge. And we'll be hearing about that from our guests tonight and then also over the next 3 weeks. In tonight's episode, we'll explore some of what we know and some of what we don't know about the science and ecology of forests and fires. Fire is a natural and expected phenomenon in Western forests. But what has that meant in the past, and how have our forests and fires changed up to the present? And then also, what does this science tell us about how we should prepare for and respond to fires? Before introducing this evening's guest, Kristen and I want to acknowledge and thank the Gates Family Foundation for their financial support for this series. And we also want to thank our partners at the Denver Museum of Nature and Science, and several of my partners up here at CSU, including the Forest Restoration Institute, where Camille works, one of our guests, the Southern Rockies Fire Science Network, the Colorado State Forest Service, and also the Climate Adaptation Partnership. With that, I'll introduce our two guests tonight, Dr. Tim Brown and Dr. Camille Stevens-Rumann. Tim is a research professor at the Desert Research Institute in Reno, Nevada, and he's also the director of the Western Regional Climate Center, which I reference regularly for the great information they provide to the public. Tim's interests include the connections among wildland fire, weather, and climate, fire management and policy, the interface between science and decision-making, and user engagement through the deliberate co-production of knowledge. Welcome, Tim.
Oh, thank you very much, John. It's a pleasure to be here this evening. And just quickly, I do have a connection to wolves because here in Reno, the University of Nevada, it's the wolf pack.
Aha. Well, given that I'm a ram, you know, I'm still thinking that our rams can hold their own against your wolf pack. But anyway, so Dr. Camille Stevens-Rumann. Camille is an assistant professor in forest and rangeland stewardship at Colorado State University's Warner College of Natural Resources. And she is also assistant director for ecological research and monitoring at the Colorado Forest Restoration Institute. Camille's research focuses on post-fire disturbance recovery, including challenges facing disturbed lands, and also how we manage forests and fires for species and the ecosystems that they support, and also how, especially how ecosystems respond to disturbance, including fire. And all of this basic and applied science that Camille works on goes towards improving how we manage our forest ecosystems into the future. So welcome, Camille.
Thanks for having me.
So Camille, starting with you, you know, as I mentioned, wildfires are a natural part of our environment. Yet last year in 2020, Colorado experienced the 3 largest fires in our history. And the single largest fire of 2020, the Cameron Peak Fire, burned almost 50% more acres than the previous record fire. So to get us started, could you share 2 or 3 key things you think we should know about what led to this historic year?
Absolutely. So I think one of the big things that we need to think about when what causes all these big fires is what causes any fire, which is we can think about as the fire triangle. It's a classic thing in both fire ecology, but also fire management. And the aspects of that fire triangle is that the kind of on the large scale is the weather and the climate, which Tim will talk about, I think, when you follow up with his response to this question. But then also the fuels and kind of the landscape aspects that are contributing to how that fire might burn. And I think Tim will show a couple of pictures of kind of some of these areas that burned this year. But one of the big things when we talk about fuel is in a lot of the fires that have happened in the past, even those large ones from Colorado, like the Hayman fire, they burn predominantly in lower elevation forests where we had contributed to a lot of fire suppression activities and really changed what those forests look like because of fire suppression. And one of the really interesting and somewhat concerning things that happened this year or in 2020 was that these fires burned through much higher elevation forests and interacted with bark beetle outbreaks, as well as just forests that are historically and today much more dense normally because of the way they grow, because of their the type of species that are growing in those high elevation forests. And so the type of fuel those fires burn through is really not something we've seen here in Colorado up until 2020, at least on this scale. And then we get into so that's one is those fuels. And not only were there lots of fuels, but also lots of all that fuel got dried out through many months of a hot, dry summer. And then the final aspect is that wind, right? You can't do much as a firefighter when you're dealing with a 60-mile-per-hour wind. There's just not very many actions that can be taken reasonably to try to stop a fire when those kind of synergies happen and you see these big spreads. And so a lot of all those things combined is kind of what made these huge fire spread days and large fires that we had in 2020.
Thanks, Camille. And Tim, you have a couple of pictures that you can share that illustrate a couple of the points that Camille just made.
I do. So we've got 3 pictures here. So I'll invite Camille to describe these.
Yeah, so this first one is from the Medicine Bow National Forest. This is a spruce fir forest. And you can see like a lot of the places on this call that people have been to have really a lot of tree mortality, right? This is a spruce beetle outbreak area. And this area actually burned as a part of the Mullen fire. And so you can see that the fuels dynamics in that forest are probably very different than they would have been even 20 years ago before all these trees had died. And also it presents a very big risk for firefighters as well. You don't want to be standing amongst all those dead trees that are now even more weakened by burning. So you can go to the next picture. So this is just zoomed in a little bit on another area on the Arapahoe Roosevelt that shows, again, that kind of intermix of live and dead trees. These trees are all very close to one another. And historically, this is how these forests would have been. This isn't a product of bad management or lack of management. This is what these ecosystems, looked like for the last several hundred years, minus maybe the dead tree component of this. But bark beetles are also a natural part of these ecosystems. So these kind of cyclical mortality events have happened in the past. And then this last picture just really shows you kind of what those fuels look like on the ground in some of these areas that burned. This again is another area that did burn in the Cameron Peak fire. And when you're faced with this kind of forest and trying to do active fire suppression, it's very difficult to get in here and actually cut logs, all of those logs, remove that fuel, change the likelihood of the fire going over the top. And again, no matter how much you try to build a fire line through this, very little is going to happen when you have 60-mile-per-hour winds because of those climate and weather conditions.
Thanks, Camille. And Tim, Camille mentioned that weather and climate several times, and you have a few overarching thoughts on what was special about last year that set us up for last year's fires. What do you think?
So I do. So I like to think about, there is a difference between weather and climate, and one of those things may be what Stephen Colbert said once upon a time, is that climate is 1,000 little weathers. Because the difference is when we talk about climate, that it's that longer term condition that enables fire. So the drying of the fuels, the curing of the fuels, versus the weather, which is a driver. So that's more of the day-to-day thing. So I've got here 3 slides for each of the big fires, and we can talk about the setup conditions for these. So this first one is for Pine Gulch, which the fire ignited on July 31st.
Oh, Tim, real quick. Can you,
Yeah.
we stopped seeing your slides. You want to start sharing again as you describe those three, please?
Oh,
Thank you. We lost it.
I'm not sure what happened. I saw the screen change, but I don't know why.
There we go. Thank you.
All right. Otherwise, that would have required quite a bit of imagination, wouldn't it? Okay, so yes, so the image on the left is the US drought monitor for the week just prior to the start of the Pine Gulch fire. And you can see over Colorado and actually over much of the West, the orange and some red colors indicating moderate to severe to even extreme drought. So this had been going on for a while, and so this was setting up the dry conditions for the fuels, because this would be also related to reduced soil moisture, which is the reduced water availability for plants to uptake, and in this case, the trees and shrubs. And so they're going to become more stressed as a result of that. The image on the right is less revealing for this particular fire, but this is what we call evaporative demand. And basically it's atmospheric thirst. And I think a good analogy to think about how these two work together for fire is, imagine a Christmas tree in your living room, and you have a bucket of water underneath the tree. You start with a live tree. There's water underneath it, and that tree is uptaking that water to keep its cells and leaves moist. But at the same time, the air in the room is warm and probably dry. And so that's taking that moisture right back out of the tree. And sometimes what happens is that evaporative demand, or that taking of that moisture out of the tree, happens at a lot greater rate than what the tree is able to uptake and maintain its health. So the tree will become very stressed by that. And ultimately what that does is increases fuel flammability. So for the Pine Gulch case, there really wasn't any kind of unusual evaporative demand prior. I would think of this event, this particular fire was lightning started. I think this is it's kind of a typical fire that could easily happen in Colorado this time of year. And the other thing that didn't happen for Colorado this year is the monsoon. The southwest monsoon was a weak event. And so there was not moisture surges that came up into the state like during years when the monsoon is more active. But now you'll see a difference for the other two fires. So here's Cameron Peak, which began on August 13th. We see that the drought conditions are certainly still covering Colorado, and they're actually even expanding further across the West. But look what's happening here to the evaporative demand. And this is, there are four elements that go into this demand. It's temperature, it's relative humidity, it's wind speed, and it's solar radiation. And Camille already mentioned early on, temperature, dry, wind, very critical factors here. And so it was warm temperatures, anomalous warm temperatures, a dry atmosphere that's really causing this evaporative demand to increase. And so it's very rapidly increasing the fuel flammability. And the last one is the East Troublesome fire. We see the drought actually getting worse in Colorado across the West, but check out this evaporative demand. That's a huge area of extreme conditions. And so if a fire is going to ignite in this, the vegetation is primed. And as Camille showed you in those images, look at the density of that fuel. And now imagine all that with high fuel flammability and ready to burn. And so that was the setup for the three big fires.
Thanks, Tim. Thanks, Camille. I'm going to pop in here, John, and toss one back to Camille. And both of you set the stage nicely. And I think there's a lot of different things that we're going to want to pick up on, including the drought and more in climate. But Camille, you did say something about forests, and I think you said this is how our forests are here in Colorado. So I'm wondering if you could speak a little bit more to what you mean by that. In particular, what are the different types of forests here in Colorado, and how do these different types of forests play into fires and the role that they have in fires? Could you just add a little bit more to that for us, please?
Yeah. So I think in the past, a lot of these places that we've even had large fires have been lower down in elevation, these kind of ponderosa pine dominated forests. You can think about the Hayman or the High Park fire, or even the 4 Mile fire being kind of this type of forest type that historically would have been more open, had probably more active fires that were low to moderate severity, burning fairly frequently, not killing all of the trees, kind of keeping a low density forest on the landscape. As you move up in elevation, you kind of transition into these different forest types. And I think Colorado is one of those places where this transition is probably more clear, and those lines are more defined than other states, just because we have that nice, think about as you drive up I-70 or go over Berthoud Pass to go skiing or things like that, those you kind of travel through those forest types. And so the next one is lodgepole pine, which historically would have had a higher intensity, higher severity fire regime that those trees are very adapted to. They have what we call serotinous cones, which is where those pine cones that you see on the tree actually open with heat and fall down, and they love that just burned soil to establish and regrow. And so, in that forest type, those fires would have happened, on the order of 1 to 200, maybe even longer time frames, and been really high severity, high intensity. And then again, as you move even higher in elevation up to spruce fir forests, we end up with these forests that, those pictures I showed, that are really dense, closed canopy forests with a mix of species, lots of fuel on the ground. And in some cases, those, on the short end, those forests would have burned on 175-year time frame to up to several hundred years. And that's kind of what we get at when we think about what was limiting versus enhancing these fires, is that a lot of times what stopped fires in those higher elevation forests before is that the climate and the weather wasn't conducive. They were moist, the snow would have stayed on those sites for much longer. Think about those years that we've had where, you can go backcountry skiing in June, right? You're still tromping around at high elevation through a foot of snow. Well, that didn't happen really this past year. And so all of that fuel, all of those trees became ready to burn. And that's, I think, one of those things as we think about, as you move up the mountain, you go from a fuel limited system to a climate limited system, meaning that at the bottom, historically, at least, those forests would have been more open and the fire would have been limited by, there's just not enough fuel to carry that fire every year or be that extreme. Whereas at high elevations, it's really been limited by climate in the past. And that's why we're concerned about, the pattern that we saw this year with that evaporative demand change and things like that, because we're suddenly dealing with a system that we would have thought the fires would have been mediated by climate are now mediated by that large amount of fuel that's up there.
So Tim, thank you, Camille. But to build on what Camille was saying, Tim, how unusual was that dynamic you described last year? Can you put that in Camille just described a sort of centuries-long dynamic. We've got the low elevation forests that burn regularly, lodgepole, maybe, what did you say, Camille, every couple hundred years or something like that, and then this high elevation forest much more rarely, every few centuries or something like that. But how, can you put that drought dynamic you described into a centuries long context. How natural or unnatural was that?
Yeah, it's a good question. So for the evaporative demand part, I looked back, the data for that go back to 1980. And I kind of scanned back through it, and it's not particularly unprecedented to have 5 periods of this evaporative demand, even into October. Well, actually, even through the winter, right? But we're talking about fire season. But I did not see one that was as bright red, covered such an extensive area as the October case did, in particular. And in terms of the drought monitor, I think if we were to take that back several centuries, sure, we're going to see periods of dry like that. I mean, across the Western U.S., actually, dry is probably favored over wet. And folks may have heard that maybe we're in or starting to be in something called a mega drought, where it's actually a century scale kind of period, predominantly dry conditions. That doesn't mean there won't be wet years in that, or even a series of wet years. But overall, yeah, it could be more on the dry side. So the West is naturally dry. Fire is a natural occurrence in the West. So these things are going to align pretty frequently. And I think it's probably fair to say as well. So like the beetle kill, for example, I mean, that's going to be partly driven by climate, as well. So that could help set up long term. So there are the natural cycles, right? That, like as Camille mentioned for that. And actually, Camille, wouldn't it be fair to say that, these periods of more excessive dry, I mean, these are going to be the enablers of naturally occurring fan replacement fires, right? During historical periods, at least pre-European settlement periods.
Yeah, absolutely. I mean, I think we do see alignment with hot and dry conditions leading to, pretty widespread fires. Even on the centuries long scale, there's some really great climate and fire reconstructions from, alpine lakes across Colorado that show a pretty distinct pattern of dry conditions leading to pretty large fires that have then in many cases actually led to, differences in forest structure, or a switch from a forested vegetation to like an alpine meadow in some cases. But I think, the key in those high elevation areas is that you have to have that alignment with like dry conditions for those fires to happen. And while it does happen, a lot of those places that we saw fires in have 300-plus-year-old trees. So we're looking at about 300-year-old fires. It's been 300 years since that last fire in those high elevation forests.
So I want to, we've talked a little bit about the conditions, right? Kind of what has led this to it. But one thing you have both briefly just alluded to, but not elaborated on, is both the human versus natural causes of quote unquote probably ignition. So I'm looking to both of you. You probably can have some words on this. Tim, why don't you start, or Camille, feel free to fight over who wants to start. What is that ratio of both human versus natural causes? And I'm wondering if you both could provide examples of what ignites these fires when the conditions are already really primed and ripe with drought and dense forests and beetle kill and all these other conditions.
Well, the most recent analysis that I've seen that takes fire occurrence data and looks at causes, especially that for most of Colorado, it would be predominantly lightning started fires at these elevations.
Camille, do you have anything to add? Or did Tim froze?
Uh-oh.
I was like, that was a really short response from Tim. There you are.
Oh, okay.
Tim, you stopped with, the last word was predominantly lightning here in Colorado. If you had more to share, please continue on.
Oh, I don't know if I did. It was probably just a brain freeze. It wasn't a Zoom freeze. It was just a brain freeze.
So Tim, do you know how many lightning strikes are there in Colorado each year, and how many start fires? And I ask that because when the four of us prepped a week ago, 2 weeks ago, we briefly discussed how good we are at putting out fires that are started by lightning. So how many fires actually get started every year? Any idea?
Yeah, I wished I'd have thought about that question before. I don't have that at the top of my head for Colorado.
Yeah, and I don't know the number that start. I think one of the stats that we had talked about is that we're so effective at putting out fires that we put out about 98% of fires that start. So it's really only that 2% of fires that make it kind of past that first 24-hour period or initial attack period to like be these large events. And so, you know, as you think about like the amount of resources and people that we employ in the United States to fight fires, they're pretty effective, even though what we see on the news does not necessarily demonstrate that. And it's really has less to do with the people and more to do with those like weather conditions that are driving that 2%, right? It's like when the conditions are so extreme that it doesn't matter how many people you put on it on that day, you're probably not going to be extremely effective in putting it out.
So we have a clarification. I'm going to pop this in here real quick for Tim from the chat, just because I think we're going to probably move off some of the graphs that we had, but while it's fresh in people's minds, people, first of all, sharing the evaporative demand and the concept of the Christmas tree, I think was really helpful. In your graphs on the right, you had EW, and does that stand for evaporative demand? And what is EDI? Is that a long form and short form? Is that the same? Could you explain that on the graph real quick?
Yes, so EDI is short for Evaporative Demand Drought Index.
Great.
And that scale was created actually initially by Mike Hobbins, Dr. Mike Hobbins at NOAA in Boulder. And it is aligned, it is scaled to be aligned with the drought monitor.
Great, thank you for that.
The colors and scale should align in that regard.
Great.
So I wonder if there's a question, we got a question from an audience member that I think both of you could reflect on here for us usefully. So fires are natural in Colorado's forests. We've got a whole bunch of questions that we may or may not get to. But the fires are natural. How those fires interact with the forest might depend on, or does depend on, what kind of forest we're in, what elevation we're at. And climate is a big factor. Climate and weather are big factors here. I wonder if you could both speak to the change in climate briefly. And so what part of what we experienced last year is, quote, natural, and how much of it, I know this isn't an easy question to answer, but if you could share a little bit of your thoughts on what we understand about how our changing climate and people actually causing wildfire starts. Cameron Peak was we think started by a person. So the role of people through climate change and starting fires compared to what we would expect naturally. Can you share thoughts on that dynamic?
From Yeah, my perspective, I think of it as the confluence of climate, people, and fuels. So Camille's talked about the fuels a bit and the role of what 100 years of suppression or fire exclusion might do, right, to help build up fuel availability. From the climate perspective, there's no question that the West is warming. I mean, the world is warming, but here we're talking about the West, and so it's warming. And there's also no question about how that warming exacerbates the drying and the drought conditions. Because the warmer it gets, that will draw moisture out of lakes, water supplies, out of the ground, out of the vegetation. And so it's a feedback process. And so we know that that's going on. And then from the people perspective, at least a lot of places in the West, there are human starts and human started fires, ignitions. And as you said, probably two of these are going to be human related if that cause can be determined. And so when I think about it, it comes full circle. I mean, it's anthropogenic, right? It's humans that are causing the warming that we're having through the greenhouse gas concentrations. And that comes back around to increasing the temperature, which increases the drying, which increases the potential for fires. So it all comes full circle. So you might even be able to make an argument that all this, or much of this fire activity, yeah, is all human related. But maybe not so much so for lightning. It's not clear if at this point in time whether there's been substantial changes in lightning as a result, or even what might happen with lightning down the road. One thought is, as the globe gets warmer, there will be more moisture in the atmosphere, which will make thunderstorms juicier and may create more lightning that way. But the extent that that will be dry lightning versus wet lightning over some of these places, I think is a big scientific question.
I appreciate that, Tim. Oh, Camille, I want you to follow on, but I want to throw a statistic in here because we were talking about it, and then you both can continue on with this and bring this in, which is my colleague Trent sent me the statistic for lightning versus human-caused fires based on Jennifer Balk's paper from the Proceedings of National Academy. She did a 20-year review. So this is from 1992 to 2012. There were, in this paper, the review found that there was about 250,000 lightning started fires, so 250,000, compared to 1.2 million human started wildfires in the US in that 20-year period. So back to kind of just making sure, like, our audience, because we brought this up and none of us had a statistic. So thank you, Trent, for finding one for us. And the proportion of human started versus lightning started is really fascinating. But please continue on with this climate angle too. And I appreciate, Tim, your comment about what we don't know about the impact on lightning. But please, Camille, did not mean to interrupt.
Well, hey, let me just clarify that paper a little bit. So yes, that's right. So, but also keep in mind that actually there are more fires in the eastern U.S., more fire starts than there are in the western U.S. So it's very geographic, where it's human versus lightning.
That's a very good point, right? And this isn't, he didn't send me the scale, right? I think these are probably total number of fires. So yeah, thank you.
Yeah, and so I was just going to add in regards to the into how climate change is playing into all of this. I think there's been some really great research recently that has talked about what aspects of fire is changing with climate change, and there's a couple. And so the first is the fire season length. Just the pure length in which fires are starting is increasing, and we see that right with for a while, I feel like even when you heard about California fires being a bad fire year, it would be just a short period of time. And now we hear it from January to December almost. And so I think if you have, one of the things, how that plays into climate is, especially in these colder forests, what we see is that the snow is melting earlier, resulting in the drying of that fuels, which makes them available and ready to burn sooner. And it's getting snowed on, and that fire season is stopping later. And so that's kind of lengthening. And I think that was one of the things that was really shocking about this year's fires, even from me, like looking who studies fires, that I was like, well, okay, it's August. All right, I still expect some fires. Oh, it's September. It's kind of late, but yeah, maybe we're still within the fire season. But when we were having those big fire runs and the East Troublesome fire in October, that's pretty rare. For this type of forest and really across Colorado. We don't see those huge fire spread times when we're moving that far into fall, which is that fire season lengthening. And then the other kind of things that we've seen in the literature anyway that we can contribute specifically to or correlate to climate change is things like the fire size is potentially increasing. Again, this is somewhat of a small window that we have data on. We're not talking about long historic fires, but at least in the last 100 years, we see larger fires. And even over the last 30 years, we see an increase in the amount of high severity fires. So those high severity areas where we see 100% tree mortality, it's just a black moonscape, which I think is important for us to remember that that's not all of that whole fire perimeter. As any of you drive out on, drive up to Cameron Pass, drive past the East Troublesome fire, you'll see a lot of green trees still. And there are, even within that big red blob of a fire perimeter, not all of that is high severity. And so that's important for us to distinguish too, even though we do see an increase in those high severity areas burned because of climate change.
Yeah, I think that's a really good point. And this is one of my pet peeves, I guess, about our fire reporting system. Area burned is the easiest thing and the most common thing that makes it in the media and actually into many analyses, including climate change analyses. But to me, it seems like what you want to know is the impact of what happened within that area, right? And that's the severity component that you're talking about.
Great. I'm thinking, John, how about we talk a little bit about behavior a little bit, because I think we've touched on it at the beginning, but we should probably talk about how fire behaves. And I'll start with one that you both is a indicator and direction of how fire behaves, among other things, which is wind. And I find extremely a very important and fascinating piece of how fire behaves and spreads. So Tim, let me start with you. And Tim, if you can move a little bit closer, a couple audience members are having a hard time hearing you. Thank you. So what do we know about how wind can spread, and how good are we at predicting? I know there's some models I've seen that try to predict wind speed in advance to apply to where potential fire could spread. So I'm wondering if you could speak a little bit in general to the role of winds and any sort of prediction we have when it comes to understanding that impact on fire behavior.
Sure. Well, you can get rapid spread. Wind is usually the factor, but not always. There are some fires that rapid spread can be terrain driven. It's just the characteristics of the landscape and then the fuel density across that landscape. And so you can get significant spread rates just from that. But yes, wind is a very common though factor. I don't know off the top of my head what some of the spread rates were for these fires, but like the Camp Fire in California, that was basically a football field a second for a spread rate. So, I mean, that's a very, very extreme event, right? As far as prediction, wind prediction for these events is actually very skillful. It's not the wind speed that's hard to predict. It's what are the fuels in a fire behavior model to have all the fuel characteristics that you need to predict. So it's the continuity of the stand. It's how continuous the stand is. It's of course the moisture of the fuels, all these different pieces need to be modeled and combined in a way that you can predict a spread rate given a wind speed. And I confirmed with Russ Mann of Predictive Services down in Denver earlier this morning that dry cold fronts with strong winds were major factors in all three of the big fires this year. So wind did play a big role there.
Yeah, and I would just add the East Troublesome moved at 6,000 acres an hour, which is pretty incredible. That's I think almost on par with the football field a second. And then, you know, I think the other thing that we haven't talked about in regards to wind and weather in those big fire events is that to some degree, these fires, once they reach a certain size, start to create their own weather. So on top of, you know, these driving more landscape scale patterns like of driving wind direction and wind speed, we start to see a lot of interplay and weird weather dynamics that happen as that like big column grows, as you see these really big fire spread days. And so that's kind of what makes it unpredictable in the moment, is that it's somewhat hard to predict how much that fire itself is going to create the weather dynamics and push the fire in different ways. And, you know, we see things like there's some terms called column collapse, which can really spread fire by starting, you know, fires in advance of the current fire perimeter, calling it spot fires and things like that, because of a change in where that smoke column is going, essentially.
Yeah, and this is a big area of study that's starting to happen, which is if you start with an area of fuel and you ignite it and you have behavior of that fuel, but it turns in, like you say, into a column, you have plume dynamics. There's meteorology with this. So there's, you know, air, the influences of the meteorology, air being brought into this. That's an emerging area of research now that's beginning to happen to better understand just how all of that is connected.
I want to circle back to the questions of fuels, and Tim, you mentioned how, you know, wind is actually relatively straightforward to predicting, you know, until we get into the complexities of the fire and the fuels and all of that. I want to get to that in a second, but before going there, Tim, do you have a sense for this dynamic you two were just describing around this really extreme behavior that's created by the fire itself, or in combination with the more regional wind patterns? How unusual were the dynamics we were seeing last year? Like, we saw the fire jump the Continental Divide in Rocky Mountain National Park. Was that really a really extreme kind of novel dynamic, or is that something we might have expected 50 years ago under the right conditions?
I'll let Camille go first.
I don't know. I mean, so again, I think we have seen droughts before. There's a possibility that those like fire and fuel dynamics or fuel and weather dynamics could have caused a fire to jump the Continental Divide. That's pretty rare, right? That negates a lot of the things that we call like fuels or fire mitigation actions. If you have a fire that's able to jump the Continental Divide, you're probably not being effective at even treating, you know, hundreds or 1,000 acres. And so in that way, it's rare because we think about how to mitigate our, you know, fire risk, whether that's like our whole community, my personal property or whatnot, as on a much smaller scale, and usually that's effective. But that has happened in the past. So I think the 415 fire also jumped the Continental Divide. So again, that's another big fire. It was not that long ago, but we do have some previous evidence that happened. Going back longer history, it's a little bit harder to know that information, just because, you know, when we talk about understanding what historical fire regimes are like, we're getting that information, like I said, from lake sediment cores or trees themselves that have recorded fire scars. And so we really have point data. And so we can't say like for sure that, you know, one point on one side of the divide versus and the other side of the divide, even though they had a fire in the same year that it crossed that landscape, right? Could have been two separate ignitions. So outside of modern history, we don't have a sense of how often that like may have happened before. So it could have happened, but we don't have my answer would be we don't have a great understanding of how often that would have happened.
So Camille, you are, let me get the title right here. You are the Assistant Director for Ecological Research and Monitoring at the Colorado Forest Restoration Institute. I'd be curious to hear from you and then from Tim as well, like what don't we yet know that is really, that we think could make a big difference in our understanding of whether it's forest management, fuels management, or response to fires? What are some of the most important things that you're working on right now that will inform how we interact with fires going forward?
Yeah, so I guess the first thing that comes to mind, since a lot of my work is looking after the fire happens, is how these ecosystems are going to recover. And that's one of those things that I think is very much of an unknown with climate change. You know, for a long time, we expected these ecosystems to come back as forests and that they would naturally regenerate. And that's something we just don't have a good sense of, especially across all these forest types that these ecosystems burned. And that has big implications for things like how do we plant, what do we plant, when do we plant the trees if we're going to try to reforest these areas. And a lot of that plays into how rapidly the climate is changing and what's a site suitable for now versus what it was suitable for even 10 or 20 years ago. So I think that's a big thing and will continue to be a big issue, especially as we just deal with the fires from 2020. I think on the in relation to subsequent fires, one of the things that we are still trying to understand is how we know that with climate change that there's a likelihood of increasing fires. We've already seen it. We've seen increasing size and severity like we talked about, but we don't know the effect that fuel will become limiting in some of these places, right? You have to have fuel for there to be a fire. And at some point, if it's burning all the time, you won't continue to have fire spread. And so I think we haven't quite unraveled that true climate and weather versus fuel limiting effects as we move into these different fire regimes of a changing climate. So I think that if I was going to just list two, that's what I would say.
And I think for me, just quickly, there's probably three areas that really stick out. One is, again, is understanding this holistic and synergistic nature between the fuels, the dynamics of the fire, the plume dynamics, what chemistry does that lead to in terms of smoke, and then ultimately the impacts of the smoke on firefighters and the public, as human health factors. The second area is I'm particularly keen on the relationships between the dynamics of soil moisture and this evaporative demand idea for fuel flammability. We have something that's been used since the 1970s, fire danger. right? The Smokey the Bear signs that you see alongside roads entering parks and forests. Well, that's fire danger. What I'm thinking more about is fuel flammability. What is it exactly that's happening that rates different levels of flammability? And the third thing is really a mix between physical science and social science. And that is, I think there needs to be some changes and improvements to the red flag warning system that the National Weather Service does. Initially built for firefighting agencies, but this is now also very much used publicly. And so just what should that system be like? And particularly as these fires, as Camille said, as the fires are, if we're getting more and they're more intense, then there's going to be more warnings, come out of that. So what should that system look like now and into the future?
This is both really good. John, I'm thinking we're getting close. Should I wrap it up with one final question, or do you have something quick you want to ask before we give them some closing thoughts?
I don't have anything quick. I have a whole bunch more things I'd love to ask. But cognizant of the time, why don't you take it?
Okay, why don't we kind of get to all some closing thoughts here? And I'm the same with John. Wow, we could have covered a lot more ground. Our audience has a lot of good questions in here too. And I will say to our audience, we are planning to cover some more of these in our future episodes. For example, we didn't talk a ton today about the WUI, which we'll hear, I'm sure. And for those of you who are not familiar with that acronym, it's a Wildland Urban Interface. It's a great acronym coming out of the science community, to be honest with you, WUI. Say it all day. We didn't talk much about today. We will in future episodes a lot with some of these other questions you have. So apologies we don't get to them. But I want to give our guests today, because you were going there a little bit with this question, because I know you both think about it, which is where are there opportunities right now for improving some of the science of particularly what we know and what we don't know to inform our wildfire decision making? So where are there opportunities, and who, I want you both to provide where you think there's some opportunities for us here. I'm going to look at Tim first, and then Camille, why don't you close out with your thoughts too?
All right, thanks. Well, the first thing that comes to mind is I think we really need, I'm in Stephen Pine's camp on the idea that science and technology, these are very important. There's lots of things that we can do there that will help aid decision support. But there is the other side of it, and that's the societal and political will, once you have that information, to implement those actions. And so what are you going to do with that information as an agency or as a community? And so this is also a very important area of both this combination of societal and physical science kind of research.
And I would say, I think one of the big things that we're going to have to tackle in an increasingly flammable world is how we use fire to our advantage. We can only do so many treatments. We can only do so many even prescribed fires. And to get the kind of landscape scale, treatment, so to speak, that we need, we should be using fire. And this is, we have many land stewards that worked on this across North America that used fire very effectively for many uses. And I think we're going to have to be comfortable with more fire use as we go forward if we really want to be effective in mitigating the potential for these large fires. And so, again, I think that comes back to that other 98% of fires that we put out right now. Those can be used. And I think there's a lot of science around that on where and how and, under what conditions is that appropriate, under what places is that appropriate, given the wildland urban interface. And all of those, I think, again, come back to a lot of what Tim said in terms of that social and political capital, as well as like our individual acceptance and acknowledgement that fire is going to be a part of this ecosystem. It doesn't matter how many bad fire years we had, we're still going to have more fires. And so it's how we can, harness them ourselves versus allowing them to be the manipulators of the landscape, so to speak.
Well, that was a great closing comment there, Camille. Thank you. Yeah, because fire is part of these ecosystems, and we are part of these ecosystems. And we'll be hearing next week about partnerships in the context of both response to last year's fires and also recovery from those fires. And then on April 5th, we'll actually have one of our guests will be a researcher who has worked with the Jemez Pueblo in New Mexico on documenting 500 years of living compatibly with fire. I know, Camille, you've worked some on that topic as well, about using traditional ecological knowledge to inform what we do today, because one way or another, we have to figure out how to live with fire. Really, really appreciate, Tim and Camille, your deep knowledge. Wish we had another 2 or 3 hours to continue this conversation, but thank you so much for sharing all your knowledge tonight, and for all of you who joined us for this evening's conversation. Thank you for taking an hour out of your evening, and please join us next week, which same time, 5 p.m. Mountain Time, same channel next Monday, and it's going to be another fascinating conversation to build on this foundation that our two guests tonight built. So thank you all, and have a great evening.
Thank you.
Thank you all.